welcome to this week's Crunch seminar. Uh, Today we have two presentations. The first presentation is Dr. Shuhao Tao. Shuhao is a computational mathematician interested in solving partial differential equations, and his PhD thesis back from Purdue University works on how to construct a posterior error estimation for Maxwell's equations for finite element discretization. Most recently, Shuhao has been dedicated to bring together the design of neural network architectures and the theory of partial differential equations. Also, Shuhao shared his GitHubs that I'm going to put it in the chat. Shuhao, with this short introduction, you can begin whenever you're ready.
Okay. So first I want to, say my great appreciation for from George, for inviting me, and also Juan for organizing, like making arrangement for all these things. And so today I will talk about transformers. So apparently, the first question is what is a transformer? And so when I wrote an SF proposal like 4 years ago, the reviewer asked this question: what is a transformer? You didn't even explain what is this thing. What's the difference? For example, with something like a pin. But 2 years ago, I wrote almost the same proposal. No one asked this question anymore because I submit the proposal, but then after that, ChatGPT came out like 2 months later, and now everyone knows transformer. So, I mean, then I don't have to explain what is a transformer. The reviewer said, "Oh, it's nice. Someone wants to study the mathematics of transformer," and so yeah. So it's all about kind of about luck. And not only transformer can be served as a language model, it can be, doing lots of things. For example, so the left one is the famous stable diffusion method that uses DDPM, this pipeline, to generate, these synthetic images with a text prompt. So, and the right is, so DeepMind embed these the state of an integer valued matrix, which is in the prime field, and into a real high dimensional like vector space, so that they can discover some faster matrix multiplication algorithm for a specific category of matrices. And of course we have AlphaFold, right? So AlphaFold deal with a very difficult task, that is given the sequence of amino acids, and the goal is to give the 3D structure of a protein, based on these sequences of amino acids. So, but what exactly is transformer is it dates back to this like translation models. So it uses the exactly same these modules. They stack them together and to solve this language translation problem. So what are those encoders? So the encoders is, in general, we call it a tensor to tensor neural network. So what it does is we can view these tensor to tensor neural network as an analog of operators. So it's a map between function spaces, and when we discretize them, think about this. So when we solve, just for the simplest example, this Poisson equation on a square domain. So it doesn't matter it's multi-grid solver or let's say direct solver like false multiple. So we apply the exact structures of these solvers on different resolutions. So no matter you discretize in a 128 by 128 grid, or you discretize it by a like 1024 by 1024 grid. So it doesn't matter, and the structures of your solvers are the same. So very similar for the for any tensor to tensor neural network is. So we want to do something similar. We learn maps between function spaces, but in the end, because we have to train based on data, so we still have to discretize it. So now let's worry about, for example, yeah, can I disable this window? Oh, sorry. So what happens is, so let's look at let's look at this guy. Okay, so so let's look at this guy. So the input dimension is an m by d matrix. The output dimension is another m by d matrix. And what happens is this m doesn't have to be fixed. Okay, so but this d is normally fixed. So the n is the size of the discretization, and this d is, in the context of computer vision, it's a number of channels. In the context of language models, it is a token, which is like a word. So for example, a word is embedded into a d-dimensional vector space. Okay. So, and the idea to this tensor to tensor is the training is done, at a resolution that is different from our evaluations. Right. So like I said, so it's so each layer is, we can view it as an operator valued neural network. So for example, so let's think about this problem. So we have think about Poisson equations. So we have our right-hand side, okay? And we have D channels, like D representations, like the D right-hand sides. And we want to get, like D output. And each output are living on the same grid. So for simplicity. And then we have our, the simplest, to compute this thing is we construct a kernel. So this kernel has this dimension, that is, so if we have n by n grid, then this kernel characterizes interaction between grid points. So so every grid interacts with, globally with the other n square. So that's why we have n to the fourth power, this kernel. So now the idea of operator value neural network, this tensor to tensor model, is we want to construct a kernel. We want to parameterize this kernel without the dependence of n. Okay, so this is the key. We don't want our kernel scale like n with number of parameters. Otherwise, it's it's not doable when our n our size of discretization become bigger. So it's basically like multi-grid smoother. Our multi-grid smoother is like a fixed tridiagonal operator. Sorry, multi-grid interpolation is a tridiagonal operator. Okay, so it's like it has only 3 parameters, but it can scale like arbitrary sizes. Okay, and now how to carry out this this kernel integration? So we have 2 ways. So think about this as a discrete. So I mean, kernel integral is nothing but a linear combination, right? So this is like our yi, like fi, and the sum is with respect to I. And so this is nothing but a summation. So then we have, in general, the operator value neural network has 2 key components. The first one is basis. The second one is how we aggregate the basis. And the first is we construct a nonlinear basis, and the coefficient to aggregate them may be nonlinear, maybe linear. It depends on applications. So then we linearly aggregate them, and the famous deep operator network is this category. That is, we use neural network to construct our bases or frames. and then we aggregate them using a linear combination. So the second way, so which is we use linear frames or linear bases. We do a linear projection, and then we non-linearly aggregate them in that this kernel depends on this instance. Okay, depends on the very instance. So they are like interdependent, and luckily, you know, so like I said, this attention in the transformer is in this category. But I do want to shout out to something OSHA and his collaborators invented 20 years ago. Actually, I learned it back in my grad school in the signal processing class when we do this, so, you know, old school, this Sobel filters, Laplacian filters in the frequency domain doing FFT. And I actually learned it. I didn't realize until maybe last year when I studied the literature that the non-local operator is in this category, you know, so this signal-dependent kernel, which is transformer, but it's if it's getting parameterized, all right? So then we continue to, you know, to present what is this transformer. I mean, I took this picture from the famous paper, Attention is All We Need and All You Need. But and let's focus on this left half, which is this encoder, is basically the building block of tensor to tensor. And at its heart and soul is this scaled, you know, dot product attention, which is we have three matrices, this query, key, and value. So, and we'll see in a moment, and what, like my personal interpretation of it, and our modification of how we more efficiently compute this attention in, you know, application-oriented this, so that our attention can conform to the structure of our PDE problem. Okay, so attention has lots of components. Okay, so the key component I want to present is this guy, so which is the scaled dot product attention, which is within this rectangle. All right, so if we write it out, everything mathematically, so we have many like key components. For example, whoops, sorry. So for example, the first one is this positional embedding. So positional embedding works like a coordinate system. So it's pretty much we add a linear or nonlinear bias to each channel and to each position. So there are lots of, in the operator learning context, there are two papers exploring, you know, these positional embeddings, and they are quite interesting. They use some, you know, like other than the Cartesian grid. So they use some nonlinear coordinate system to characterize the specific problem they are interested in. So this is our scaled dot product attention. And and let's skip this slide. Okay, so there are many other components such as layer normalization. And so here I want to like make an advertisement like thing, because I want to have more mathematicians to jump on the bandwagon to study the attention. Like it's still an open problem, even though everyone uses large language model right now, you know, this generated pre-trained transformer. And but how attention works is still an open question, in that there is no specific data set or experiment designed to explain how attention works. So there are explanatory like works, how attention works, but there is no definitive you know, experiment design, data set design to explain this. Okay, I mean there are lots of interpretation, but none of them are design has a specifically designed data set to explain how this works. And there is an important aspect of this attention is a positional embedding. So positional embedding is is like a coordinate system. It's like a nonlinear coordinate system. And so each channel or each embedding dimension is like a sinusoidal function. And for different channels, so we have a different frequency, all right? And it's quite cool. And I do want to shout out to also this the deep operator network paper that, for example, it is the first paper to treat, the latent representation at the basis. So instead of treated row-wise as, like a word, like the traditional large, the natural language processing community. Okay. So the idea is the positional embedding can be viewed as a coordinate, and it's being studied mostly in the vision transformer paper and their variants. Okay. And also it's an open problem of how positional embedding works. It works in a very mysterious way, even though we know it's indispensable, but it's still, not well explained. Okay. So now let's back to the scale dot product attention. So 3 years ago, I wrote a paper on, applying some linear algebras to this, and we can rewrite this attention right here, this attention operator, this nonlinear operator, as like OSHA does 20 years ago, the signal or instance dependent kernel map. Okay. So then the learning becomes how to learn a better representation so that this equation is kind of satisfied. Okay, so this is like a linear algebra. So then the attention, so back to this question, tensor to tensor map. Okay, the tensor to tensor map is how do we parameterize? So this matrix is n by n. This matrix, n by d, this matrix is m by n. So n is like our n squared in the 2D example. And this matrix is n by n. The question is, how do we parameterize this n by n matrix, but without the dependence of n? So attention gives this parameterization, that is, it uses the interaction between the representation with itself, okay? Construct this kernel to characterize how different position interacts. It's very much like our old school Galerkin method. So then we can use another way of aggregating. So the aggregating is done through different channels. So this is the aggregation. So the interaction, this kernel matrix is parameterized so that it's like an interaction between positions. Okay, so we can have another type of this interaction, that is, we measure the interaction between different frames or bases. Okay, so and we call it Galerkin attention because it's nothing but a learnable Petrov-Galerkin projection of our representations. Okay, so let me let's see. Let me skip this. So it's nothing but it's this Galerkin attention is nothing but inspired by this Fourier transform. So if we compute the partial sum of Fourier transform, it's nothing but a Galerkin projection. Okay. Yeah. Let me skip this. Let me skip this as well. And okay. So let me skip this as well. Yeah. Let me move on to. Okay. Here we go. So so the first application I want to talk about is, so I believe in the audience, all the audience are experts of, the PDE operator, how to learn a PDE operator. So I'm going to maybe say the application we're interested in. So basically we're interested in learning a map between the parameter of a diffusion equation and with the solution of this diffusion equation. So this is a famous example used in the operator learning community. That is, we have a model problem from this porous medium. All right. So we have this model problem from the porous medium, and A is some non-smooth coefficient that can be constructed by a push-forward map, like of a simple function, but then the distribution is, for example, so let me first say the problem. So the problem is, so we want to through a deep learning algorithm. So we want to learn the map between the coefficient and the solution. You know, in traditional, if everyone have learned the finite element, we know that in terms of Hilbert spaces, this is a well-defined map. That is because the solution is unique based on Lax-Milgram lemma if A is uniformly positive in our domain. And so our training pairs is nothing but the coefficient to the, you know, like to the solution. All right. And this is our last function. So I do want to shout out to one of our collaborators. He said we should add an extra, you know, like physics informed loss. But this loss is implemented, okay, in the frequency domain. And in the frequency domain, why it's nice is because by possible identity, the integral is exact. Okay, so on a uniform grid. So we use this extra, this H1 loss in the frequency domain, and we find it's nothing but we weight the higher frequency with a bigger weight. So that's the trick. And so this is the first sample problem, which has been popularized by this Fourier neural operator paper. And so the coefficient is a push-forward map of this guy. So this is the inverse. So this covariance matrix is the inverse of the Newman Laplacian, okay? And with homogeneous boundary, Newman boundary conditions. So when we invert this map, so this Laplacian is very smooth, and the covariance is kind of smooth. But what is implies is so we have this pattern, and once we get the push forward map is so at a point. So most likely it takes one value, but it has a random chance to jump to another value. So that's why we see this, you know, like a random shaped coefficient. And basically we solve the diffusion equation with this as our diffusion constant. So this is our second example is the multi-scale elliptic PDE. So and our A, this coefficient, is constructed by this expansion. So so the idea is, and our data is generated on a really fine this reference grid, and we can see the solution is pretty non-smooth. So comes our first topic of attention. So how we parameterize, okay? So how we parameterize this attention. So remember, so for simplicity, we can view this attention as, so this is D, this is N, this is an M by M matrix. So we want to parameterize our attention, this M by M matrix, without the dependence of N. So now the first idea, you know, to make this computation, so we have to compute like a matrix product that scale like order N squared. This is not preferable. So what we want to do is the first idea is we use the idea of multigrid, you know, the hierarchical matrix. So to simplify this computation to this N log N complexity. So the idea is, you know, we downsample if we use the term reduce here, okay? And so after reduce, we compute the tension only based on the local windowed attention. So so the windowed attention is like we don't compute the global interactions, Okay, we only compute, for example, a point with its neighbors, but we span this window attention on different levels. Okay, so that when we aggregate them back, the interaction computed is still global. Okay, so so we did this. So we use this attention, and we stack a few layers of these, and we apply them on this on the two sample problems we have. So first one is this Darcy porous median, this diffusion equations. The second one is the multi-scale, this coefficient. So and we do want to shout out that this hierarchical attention neural operator performs best, and but not by a wide margin. I mean, so, and of course, its evaluation time is more efficient. It's like n log n. Okay.
One question, Shuhao, in this case, when you say L2, you mean the relative L2, or is like, oh yeah, the relative L2. So you have errors of 21. Okay.
Yeah. So I mean, it's nothing compared with traditional numerical solver, but I mean, I'm not specifically like proud of this, because we're currently working on improve neural operators to achieve like 10 to the negative 10 relative error, and like the traditional double precision solver has. But yeah, so for the forward solver, the accurate. But now let's talk about inverse problem. So
can you go that down to 10 to the minus 10 with single precision?
Yeah, of course. But you have to do something else. You can't sit in your neural operator and expect it to do 10 to the minus 10. You have to rely on, for example, something like finite element method, Yeah,
Oh, okay.
you have to build your finite element method into your neural network. Otherwise, there is no hope to achieve traditional numerical solvers accuracy. But that's my take. Yeah.
Yeah, but even if you try to impose like some kind of constraint inside of your network, for instance, let's say that you want to do something simple, like you want to create
no, there is no hope. So within the neural network approach, I don't think anyone can achieve 10 to the negative 10. That's my take.
Yeah. Okay. Okay. Thank you.
Okay. So the second problem I want to talk about is inverse problem. So luckily, inverse problem doesn't require lots of, like a 10 to the negative 6 digits of accuracy. So we have lots of, room to play with. And the problem we're interested in is called the electrical impedance tomography. The idea is pretty simple. So for example, I took this picture from this paper, and this baby, so we don't want to shoot like high energy rays, like I don't know, CT or X-ray through the body of like an infant. So what people do is they exert a changing current on the boundary of a body, okay? And then they measure the voltage. Or the other way, they exert a voltage, like on the boundary, and then on the boundary electrodes, they measure how the current changes. And based on this response, the people want to get a reconstruction of the conductivity constant inside. So this is basically electrical impedance tomography is and if we talk about PDE problems, so like I believe everyone is an expert in PDE, so I don't want to spend too much time explaining this. The forward model is nothing but a diffusion equation, okay? And this sigma is our diffusion constant, but the physical constant it's basically the conductivity. So, and the forward problem is we solve based on a Newman boundary condition with some compatibility condition, imposed. And then after we do a forward solve based on the Newman condition, we restrict our solution on the boundary, we get the voltage, and it is it is our Dirichlet boundary condition. So the forward map is nothing but, given a sigma, given a fixed conductivity, because we can solve the forward problem as many times as we want. So we can get the full spectrum of this Newman to Dirichlet map. So the forward problem is coefficient to the Newman to Dirichlet map. Okay, and the inverse problem is, of course, the inverse. So now the question is, this map is extremely ill-posed. So if we are, because the forward problem is just too smooth. It's too smooth, and then like people like Caffarelli or Colton, so they prove this log stability, of this inverse problem, and which means it's pretty much ill-posed, even though it has this unique solution, but it's pretty much ill-posed in that the dependence is the log of the change, which we change a small, the log got magnified like 100 times. And like many years ago, not many years ago, like around 5 years ago, so the paper by Lexing and his postdoc, I think it's on arXiv around 2019. And so they construct a neural network. It's basically a convolutional neural network to approximate this Newman to Dirichlet map. They treat this as an infinite dimensional matrix. So my interpretation. And it's like a recover this infinite dimensional matrix using like the first 30 rows and 30 columns, okay? And this is a nice work, but in reality, we want to get our hands tied. So we put an artificial barrier to this problem, that what if we only have a few measurements of the boundary data? So for example, like we said earlier, right? Given Newman data, we can do a forward solve, we get the Dirichlet data. So this is one pair. Now what happens if we only have few pairs? If we only have few pairs of data, and based on these few pairs of the forward solve data, we want to recover our conductivity. So this is our inverse problem we want to consider. Okay. So of course, we want to apply a deep learning pipeline. So this is like a deep learning to rescue. Okay. So the idea is in Lexing's paper, they want to learn an operator, this infinite dimensional operator, Newman to Dirichlet map. It's like recovering an infinite dimensional matrix using the first 30 columns and 30 rows. But here, if we only have 3 data pairs, this is like we recover our infinite dimensional matrix using the first maybe 1 column or 3 columns. Okay, so the answer, of course, is it's impossible to do that. Okay, but when it's possible is when our data follows certain distribution. Okay, when our data follows certain distribution, we are not learning an operator anymore. We are learning an operator valued neural network such that its input and output follows the distribution of our data. So it becomes, so suddenly it is from an ill-posed problem, it becomes an well-posed problem, or say well-conditioned problem, for us to investigate. So then this is our question. So the first question is, what is the appropriate, data we fit into our neural network? And the second is, what is the suitable neural network we want to, consider? So of course, the answer everyone already know. Like the answer to the second question is we want to use transformer to do the, to parameterize our deep learning model. So how about the first question? So here, the first question, the answer to the first question is we want to learn from the traditional methods wisdom. I think this is also the message I want to carry. That is, I mean, I'm a fan of finite element method, spectral method, For example, I read Professor Karnadakis' book back in my grad study. I like that book a lot. And so I'm a fan of traditional methods, and the message I want to carry to everyone is we want to use the traditional wisdom, from the traditional numerical methods to deep learning. So what is the data we want to use? We use the data from, construct the data from direct sampling method. The direct sample method by this Chinese university at Hong Kong, this Jun Zhou and his collaborators, and some guy from University College London. And what they do is the boundary data is too limited. The boundary data in 2D is like 1D. So how do we get richer features? Is they construct the harmonic extension to the inside. And how to construct the harmonic extension? Okay. Is you compute this difference. So this is the true Newman to Dirichlet operator, when we generate the data. This one is like this is nothing but a Poisson equation, like with a constant coefficient. So this sigma 0 is our background conductivity. So this is nothing but so this operator can be pretty much approximated very fast, for example, by FFT applied on a tridiagonal matrix on a finite difference grid. Okay, so then we use this at the boundary data, at the Newman boundary data, and this operator already encodes the information of sigma, which is our conductivity, like this image, and then we harmonically extend it inside without sigma, because sigma is on. Okay, so in the end, we want to recover sigma. So we get these smooth map, very smooth, but the sigma's information is hidden deeply inside. So the inspiration is direct sampling method. Okay, and in the direct sampling method, they construct this this inner product. So this D is called probing function. So this is the gradient of the harmonic extension. The bottom one you guys can view as normalizations. Very similar to the normalizations in the transformer in the tension operator. So this normalizes this guy, and this normalizes the probing direction. And the idea is this index map will achieve. So when we choose the right, like the harmonic extension, using the right frequency, we can recover, like so it achieves like I wrote here, the Gaussian-like density. So it's like in the inclusion, we'll see this kind of Gaussian bump around there. And so we want to draw inspiration from this. Of course, we borrow the the operator learning framework again. So we generate the features using this direct sampling, this harmonic extension, and then we want to learn this index map as accurate as possible. Okay, so this is given like several instances. For example, so these are the harmonics maps, and we want to learn an operator. So purely data-to-data approach back to the shape of the inclusion. Okay. So here we assume the inclusion only takes 2 values, so the problem won't be too difficult. And why we borrow deep learning is direct sampling handles a single measurement. But with deep learning, if we have different measurements, we just treat them as different channels. So and then everything go through. And so this is our assumption. That is the probing direction. The probing direction works like a query, and we parameterize it using this attention kernel, and we make this simple assumption. So originally, if we look at the probing direction, okay, the probing direction, which is we can like compute its norm using this harmonic extension. So the probing direction is taken as this local one. It depends only locally on the gradient of this phi, which is harmonic map. But now what we make this assumption is we assume it's a vector valued kernel integral depending globally on this gradient of this, okay? And if we make the assumption, we parameterize this guy using attention. And so the idea is basically this is like one attention layer without the skip connection, okay? So, but with normalizations. And the normalization is done in a very different way. So using the traditional, so it's like an inverted Laplacian matrix, and then we divided the norm. So we made several changes to the attention to fit the 2D. I mean, it's standard practice, but we make this change, okay, the interaction. So we call this attention. So people like to call this attention like a cross attention, but a cross attention is like the fine representation is interacting with coarse interaction. But here I would like to call it a cross-level attention. The reason is because the aggregation is done slightly differently. So remember, we said how we aggregate them. So in previous, our work is we use this hierarchical decomposition. So this one is we have sort of, or we have a good basis, you know. We have this harmonic extension, a very good basis. And what we would like to do is we compute how to aggregate them is we compute the interaction between different levels, okay? So this is like, again, this is like channel attention, but we aggregate their interactions on different levels. So I call this cross level attention because the interaction is aggregated on different levels. But in the end, this matrix is of the same size. It's for example, if this has D channels, then this is a D by D matrix, okay? Okay, and we prove this, you know, like a little theorem that because the interaction is nonlinear, so we can represent higher frequency data just based on low frequency representations. So I mean, it's using standard proof of this separable kernels. I mean, it's nothing too fancy, but it's a nice theorem. So of course, and now we apply, you know, we apply this our neural network to this EIT, this model problem. So basically, we have a bunch of inclusions. So so the problem is like this. So we have a bunch of inclusions, and our data is, you know, we generate this data using traditional finite element solver, and we get like the harmonic extension. So from the harmonic extension, we want to learn this inclusion. So this is the result. So we compare with several different, you know, like transformer model. So for example, the cross attention, this UNet-based transformer is the attention is computed between coarse and fine levels. So it's kind of not that efficient, but so we use. So this is our example, and this is the picture of reconstruction for on-scene examples. And so this integral-based, this transformer, so this cross-level attention performs the best, and the Fourier neural operator performs kind of bad because it truncates the frequency and doesn't work very well in this case. So because we generate our data using some higher frequency information, so apparently truncating is not a good parameterization. So now there is a caveat, but there is a caveat that so the direct sampling method is very noise robust. However, deep learning is not. So we have to artificially add the noise during our training, to get a good reconstruction. So for example, this is no noise on the boundary. And this one, even though it looks not almost the same, So we add a 20% Gaussian noise on the boundary, and this is what's inside it looks like based on this inclusion. So, I mean, even though this is very small, we can see the magnitude. This is the relative magnitude. It's kind of very small. And however, if we don't add a noise to our training, this totally breaks down.
This is Lulu. I have one question. So for B, can you explain why do you specifically add noise? This looks quite similar to me. Can you explain?
Because we want our method to be robust to noise. So this is the reconstruction with data. We add artificial noise to the data. We train we train our model with artificial noise. But this one is we train using clean data, using this, but then we give our neural network this data, and it produces absolutely garbage. Like nothing is, I can see nothing, So, and then luckily, so this is an ongoing work. So we're gonna submit this paper soon, and we can use, CS people invented a very nice pipeline called DDPM. Okay, I mean, people use it to generate high fidelity images. So it's like from noise to image is like it's like we draw a random sample from a really high dimensional vector space, and then apply this SDE like a process, we can get back to the origin. Okay, so then we have this we apply this to the EIT problem. So this is the trick. Okay, so the EIT's noise is like original. So the Euro noise assumption for the for this inverse problem is we have noise on the measurement. But for the DDPM, if we want to apply the DDPM, is we add a noise, artificial noise, to the ground truth, which is this guy. So we perturb, the conductivity. Then we apply a forward stop, okay? And to get like a noisy image, and then we get a noisy output. And then the inverse problem is we try to denoise. So we plug in this pipeline. The only thing we have to implement is we just have to implement a traditional numerical solver that can solve this problem in, disguised as a neural network, so we can plug in the auto differentiation pipeline. And it works quite good, So the only thing I did is implement a traditional solver using the PyTorch NM module. Okay. So these are the reference and acknowledgement. And also, if you like to play with the code, it's mostly in this repository. And this is I implement recently like some auto differentiable solver. So basically what I did is Google implemented a Jack CFD, but I don't know how to debug it. So I put everything back to Torch so I can view all these tensors, intermediate tensors. And these are some references. And I would like to thank NSF as well.
Oh, okay. Thank you so much for your presentation, Shuhao. It was really interesting and informative. Do we have any questions from the audience?
Yeah, may I? This is Kostas Chetos from the University of Naples. Thank you for your talk. I appreciate it. A couple of questions. The first one, how sensitive is your structure on the hyperparameters, and how difficult it is to optimize it? And the second is because you for example, the dimensionality of the bendings that you mentioned. And the second question is about the denoising. So you assume an a priori knowledge of the noise distribution, but in some cases we have color. So is there any chance that your network is focused on learning the color noise instead? Thank you.
Yeah, so let me answer that noise question first. So the noise question is, you are absolutely correct. I assume a priori knowledge of my noise, and this is like a primitive test. So if the noise is somewhat unknown, we have to apply this Bayesian inversion framework from Andrew Stewart. So we assume the noise distribution is unknown, and you have a surrogate model, and you have measurement, but you do have a prior, and based on, so you do have a prior, and based on the measurement, based on like, for example, the likelihood, and you adjust like your prior to get the final estimate of your distribution. But as of right now, we didn't try this, but this is totally doable. This people have done this Bayesian inverse problem a lot based on neural network based surrogate model. But so what we do is like a very primitive like toy model, just try to use this DDPM.
All right,
so
fair. Okay.
yeah, this is a trick. And with regarding the hyperparameter, so how do we optimize a hyperparameter? The answer is the operator learning problem.
And how sensitive it is?
Yes, that's a very good question. Let me tell you why. So if we use where was that image? So the fancy image we had. Okay, so if we use neural network to represent a function like pin or deep reads, whatever, this is somewhat, I believe, an ill-posed problem based on lottery ticket hypothesis. But for operator learning problem, if we want to use neural network to represent a distribution, this is a well-posed problem. My experience is operator learning problem with the right data, especially, for example, higher frequency got chopped off, It's not sensitive to hyperparameters at all.
Right. So the keyword here is the correct data, right?
Yes.
Yes.
yes. The keyword here is the correct data. So even though I present this as, a neural network presentation, but I do believe data is more important than the neural network.
Yeah, that's clear. All right. Okay. Thanks. I appreciate it. Thank you.
Yeah,
Hi, can I ask a question?
please.
My name is Vivek and I'm a PhD student working with Professor Kaniadakis. So I had a question about the hierarchical attention operator. One of the slides you showed at one of the earlier slides, I guess. Yes. So can you explain what's the difference between the green and blue layer? How you went from the green to blue?
Okay, so first is the local attention. So windowed attention is like if we use an n by n grid, for example. Okay. So if we have a pixel, for example, traditional attention have to attend or just compute the pixel's interaction with every other pixel.
Yeah.
Right? So including itself. But now what we do is we apply a small sliding window, we compute the interaction with neighbor pixels. But this is just one level.
Okay.
So the reduce is nothing but a learnable like downsample map. It's nothing, like fancy. Yeah.
So it is just max pooling or down like
no,
max pooling,
not max pooling. We use a learnable bilinear interpolation.
Sure, bilinear interpolation.
It's similar. Yeah, it's similar.
Yeah.
So
all right.
But then if we apply the window attention again, right? So the window is now on a coarser grid, but it's if think about this. So if
I understand.
So then the window on the finer grid, so if we fix the window size on the finer grid, it's two, the window becomes 2 times. So if we do hierarchically this, the computational complexity of this, like, so let's say this is square root of n square root of n, and square root of n times square root of n.
Yes.
Sorry, this is m by n, right? This is m by n, and this is n. So so this grid size is square root of n. So the number of points is n, and so this this matrix multiplication is order n squared. It scales quadratically with respect to the number of points. But if we do this hierarchical decomposition using window detention, this is reduced to n log n.
Okay.
It's pretty much like a Fourier, your fast Fourier transform.
Thank you.
Shuhao, you show the theorem for the frequencies.
Okay. Yeah.
But is there a theorem for? Do you have a theorem for for transformers to be universal approximators?
Unfortunately, no. I don't know how to form a universal approximation theorem. I try to modify the proof in your paper, but somehow, so there is a little bit unclear about, because in the deeper net universal approximation, so it's quite it's quite simple, because
but the FNO, maybe the theory of FNO that they have
so
now.
you have this aggregation, but now the difference, the different, like the difficulty, and this is regarding the channel dimension, sensor dimension, and but for that, I don't know how to, unless I already assume the current frames form like already a universal this basis. But that doesn't tell us much, right? So in the current latent representation, I already have a good basis. I apply this kernel, it's another good basis. So I talked to Long, who's my postdoc advisor, and he agreed that it's not worth putting it up. But yeah, but I don't know anyone has this universal approximation theorem of transformer. But the idea is we can have, so the application, so there is a theorem. Let me give you the current theorem I have. The current theorem I have is given like the current frame. Okay, so given the current frame, so this is like a vector kernel. So I from 1 to D. So this has already a good. So for example, if we want to approximate a compact subset in a function space, and if we already have, this, for example, we do some sort of projection into this U equals the convex combination of this. So if we already have this,
yeah,
I can prove, the attention integral, this kernel is well approximates well of this, but Long said it's like cheating, so I didn't put it into my paper. But I don't know, like a general version of this universal approximation theorem. I think it's very worth pursuing.
Yeah.
George, may I interrupt for a while?
Sure.
Yeah, it's Chieh from Brown University, so they're a PhD student. So I believe that I sent this in the chat. Someone from Google Research has proved a version of universal approximation theorem for transformers in 2019 or 2020. And they did this for the decoder-only structure. I'm not quite clear if this is also some version you can do this in the encoder-decoder structure, but it's also, well, at least that's not impossible, I think. So there is some results there.
I read this paper, and their sequence length, so their approximation, it's a universal approximator from this function to
right
this so to this. So
yes.
it's not really an operator universal approximation theorem.
Yeah.
So yeah. But
there are
yeah.
certain, there's a certain way they had as you mentioned, a sequence to sequence. So I guess perhaps this is possible to kind of decompose maybe the input to get you something. But I mean, it's just something possible, I guess.
They call it operator. Actually, Lulu is here on the call, and he remembers that when we wrote the DeepONet paper, the reviewers asked us to compare against sequence to sequence because they consider it as an operator. I don't consider sequence to sequence an operator, but at that time, that's why we added in our paper. There is another, I think, Handy from WPI, Handy Zhang, shows a paper, I think the people from Hong Kong, who show that they can write the transformer as in terms of CNNs. And then, of course, CNNs are universal approximators, but not in the form of an operator. That's the other work that I know, but I'm not sure.
Okay. Do we have any other questions from the audience?
Well, thank you very much, Shuhao. Thanks for taking the time.
Yeah, thank you.
Yeah, it looks
Thank
like
you
we
so
do
much.
know. Thank
for
you so much,
giving me
Shuhao.
the
It was a
chance.
really nice
Yeah.
presentation. We have a second speaker today. Jesse, are you around?
Yeah. Yes, I'm here.
Hi.
Hi. Hello.
Yeah, thank you
Hi,
so much for
Jesse.
joining us today.
Hi. Thanks.
Could you please try sharing your screen?
Oh, yeah.
Jesse, your background is scary. The cats are too big.
Yeah. I mean, she's my cat, and yeah.
Okay. Okay.
Like she's
Well.
like, can you see my screen?
Yes, we can see your screen. Well, maybe you can try to switch it to the other screen. Now we see the presenter.
Oh, well, no. You see?
We see your screen, but we see the presenter mode. Yeah, now it's good.
Yeah. Oh, okay.
Yeah. Okay. Okay. Jesse, welcome to this week's Crunch seminar. Okay. We have a second speaker today. Oh, we see the presenter mode again.
I guess it will reflect the right one later, but.
Yeah, now it's good. Now it's perfect.
Okay. Cool.
Yeah. Right. Okay. Well, we have a second speaker today. His name is Chieh-Hsin, but he prefers to be called Jesse. He obtained his PhD in mathematics from the University of Minnesota in 2021, and currently he serves as a scientist at Sony AI and as a visiting assistant professor at the Department of Applied Mathematics at the National Yang Ming Chiao Tung University in Taiwan. His research focuses on theoretically explainable deep generative models, with a particular emphasis on diffusion models and their application to inverse problems. For more information, I will also provide his GitHub on the chat. Jesse, welcome to this week's Crunch seminar, and with this short introduction, whenever you're ready, you can start.
Yeah. So yeah, first, thank you for having me here, and it's really my pleasure to like communicate with you and also share our works about the diffusion models. By the way, can you hear me clearly?
Yeah, we can hear you.
Okay, cool. Yeah, so first I would like to introduce you about our my co-authors, and this is me, Jesse Lai. As Juan was introduced, I got my PhD from University of Minnesota 2021, and then now as a research scientist at Sony AI. Okay, and today's my sharing will cover from the diffusion models itself, and also two issues of the diffusion models, and how we solve it, about the two issues within the FP diffusion work, and also recent work considering Chieh-Hsin model. And given the time restriction, perhaps I won't touch the last part, but I hope I can fastly share the key idea of that. All right. So for generative models, in general, it is we have a very complicated data set, and also it's complicated infeasible data distribution. And what we can do is like we starting from a simple trier, say a Gaussian, and use the neural network to reshape it. And then we hope the model distribution, which is the P data, to be as close as to the data distribution as possible. So roughly speaking, we are doing this kind of minimization problem. Right. And how people design this neural network and model this map, the history is quite long. So, let me erase it. Yeah, so from back to 2015, there is a normalizing flow, which they construct the so-called format, bring from the simple prior distribution to the complicated model distribution by like a sequential invertible map. And this is the normalizing flow. And if we prepare infinite many layers of this kind of bijective map, this becomes the neural ODE, where the flow, the ODE flow will bring this simple prior to the complicated model distribution. And score-based diffusion model is one type of, in general sense, it's one type of neural ODE, where they use this kind of spatial the spatial structures ODE as the format. Okay. And I guess you may be familiar with the diffusion models, but here just a brief recap. Like for the diffusion model or like score-based diffusion models, they have two processes. The first one is called the forward process, which is gradually adding noise to the data, and then make it close to the prior distribution, which is the simple distribution. And the task of the diffusion model is like trying to reverse this process for generation. However, if we prepare infinite many layers, just like a normalizing flow becomes the neural ODE, this will give us the stochastic process, which is a SDE. Okay. So far, so good. So to make it more precisely, like there are two processes. One is the forward process. Some people call it as noise injection process or diffusion process. But no matter what, this process is fixed. And what does it mean is like in the noise injection procedures, how we input the noise can be decided by the users. And some two typical examples are like binary process, where we have the zero drift term and square root of the noise injection term. And the other one is OU process, where we have kind of the linear drift term and the square root as the noise part. So once you decide the FT and GT, this gives you how you injecting noise to the data and then gradually bring it to the this kind of very noisy density. And essentially, we hope this guy can be as close as to the prior distribution, which is usually picked as a Gaussian. All right. So this is the format. The forward process. And as you may know, that once the forward process is given, the Anderson paper proves that when F and G are given, there is always a reverse process bringing from the noise to the data. And this reverse process, some people call it a generation process or denoising process. No matter what, the process is also an SDE, and you can write the equation down like this. So you can see that the FT and GT are given in the forward process, and also here the GT is given, but there is a term over here which is the gradient x of the log density. And people call this term, I mean this guy, as a score function. Okay, so the nuance is here. Like once you fix the for process, the density evolution is also decided by the given ft and gt. So overall, the reverse process has has a kind of a closed form. I mean, we know the coefficient of drift and the diffusion. Okay. However, like when we want to do the sampling, we usually starting from picking a random noise, say the noise like this, and then trying to solve the SDE backward in time. So roughly speaking, we are trying to use Weiber solver to solve this SDE reversely. But you can you can see that here we have information containing the unknown term, which is the score of the marginal density of PDE. So what people do is like they use neural network to approximate that guy. And here the trick is called the denoising score matching, where they use the condition on the clean data, the score of condition on the clean data as a training target. And why they are using this is just because we have a closed formula to compute this if the noise injection is Gaussian. Okay. So far so good?
I think so.
So once, sorry?
Yeah, that's good. That's good.
Oh, okay, cool. So yeah, thanks. So once we train the neural network as data to approximate the condition score or the score itself, we can just plug in to the SDE. And when we want to do sampling, we just random initialize with a noise and then run the SDE backward with any solver. So we can get the generation data. Okay, so up to this point, it is how diffusion model works. And this process, this framework is very neat and clean, and it is from Yang Song's 4SD paper. And besides this stochastic process, they also found that, there is a deterministic process, which is an ODE, that has the same density as the SDE process, and they call it as the probability flow ODE. Okay. So they share the same density, and the density is guided by the so-called Focal-Planck equation. All right, so when we want to do generation with different models, the procedure is like first we use the denoising score matching to approximate the score, and then plug in either to the SDE or ODE, and then when you want to do sampling, you just randomly sample some noise from a Gaussian, and then run either SDE or ODE backward in time with any solver. Okay. So the score SDE paper is quite impactful in the sense that it bridged the kind of a classic diffusion model with the ODE solving, which has a long history, and mathematicians have already been doing a lot of work to do this kind of ODE solving or SDE solving. Okay. However, there are two issues of diffusion models by nature. So the first issue is it may have the inaccuracy in the training. Okay, so here I put the illustration here. So if in high dimensional case, the prior distribution, which is taken as Gaussian, is concentrated as a shell like this, and there are multiple layers of shell because of we have multiple layers of time. And when we want to do a sampling, we are actually grab a Gaussian noise like here, and then solve the ODE or SDE backward to the data manifold, which is believed to lie in the lower dimensional structure. And when we do the differential model training by the denoising score matching, when time is very close to 0, which means when time is very close to when the score t is very small, the neural network approximation may be inaccurate because there is a sink over here to the lower dimensional structure. And this is happening during training and also for sampling. Like this equation, this SDE or OD is actually very stiff during, when time is small. So there is a kind of essential issue of the diffusion model when time is small. Okay, so this is the first issue. And the second issue is the diffusion model sample is known to be very slow. And why it is slow is because here is the forward process, and the reverse process is actually doing gradually transform the noise to clean. So I emphasize the gradually over here, and gradually means is may drag the process to be slow. And actually, we can view it in a different point of view. That is from the ODE solving. Like say, if we take this simplified probability flow ODE, essentially we are doing this kind of thing. Like we render in sample a noise as the initial condition, and then we use the slope information to gradually approximate the trajectory. So as you may know, like the classic solver need to do some discretization, and if the discretization steps usually is very large. And in the diffusion case, people were using thousand step to get the accurate generation. But no matter what, there is always a discretization errors, and there is always a trade-off between the sample quality and your speed. All right. So up to this point, I introduced the two issues of the models. The first one is inaccuracy when time is inaccuracy approximation when time is small, and the second one is very slow. Okay, so runs a bit. Right.
Yeah, good. Thanks.
Okay. Yeah. So our work is trying to address these two issues from quite similar perspective. The first work is called the FP diffusion. The FP means the Focal-Planck. So overall, the high level idea is for diffusion model itself, there are some underlying mathematical structures, but in the classical, what I mean by classical means 4 years ago. But for the classical diffusion models, their training is only depending on the denoising score matching, which doesn't consider the underlying SDE or ODE or PDE structures. So if we consider the underlying structure into the diffusion model concept, we perhaps can improve the diffusion model itself. And I call this kind of injecting the underlying mathematical structure into the diffusion model as the consistency type models. And our FP diffusion is one of them. That is, we impose a similar type of Focal-Planck equation for the score functions, which is looked like this. I will introduce it later into the diffusion model training. And we found that it can improve the data density estimation. And other institutes also, simultaneously found that there are several underlying structures that we can impose into the diffusion model itself. The second one is from UT Austin, which is called the consistent diffusion model. They impose some martingale property on top of the diffusion model itself, and then they found that it can improve the sample quality. And the other one is from OpenAI, also from Yang Song. I mean, they try to make the diffusion model sampling fast by learning some semi-grid structure of the OD, and they found that they can indeed make the diffusion model sampling in, 2 to 4 steps, and this is another type of consistent notions, right? However, we found that even though they share the different purposes, they are essentially the same. So the next question will be whether there is a unified framework that we can achieve all of the purposes, the empirical purposes at the same time. And this comes with our third word, which is called the consistency trajectory model, in short, CTM. All right. So I will first share about the FP diffusion, and then briefly talk about the more like a theoretical insight about the equivalence of these 3 different consistency notions. And if I have time, I perhaps can touch a little bit about the CTM. And I guess I saw a question. So,
I think that yeah.
Yes, I put a paper we have from my co-author who actually wanted to listen to your talk. And the question I have for you for the Focal-Planck, how high in dimensions do you go?
Yeah, so in this case, we tested on at most 32 by 32 by 3, which is the CIFAR 10 data set.
Yeah.
Yeah, and but it is actually very expensive because you can see that there is divergence everywhere and like gradient everywhere. So yeah, actually it's quite not scalable in this sense. So the 32 by 32 by 3 dimension is tested on 4 3090 GPUs, but I guess for more like advanced compute resources, we perhaps can do higher dimensions.
So in the paper I put on the archive we have on the archive, which I put in the chat, is actually for scalable.
Oh,
we use pins, so you may want to take a look at that.
Yes. Yeah, actually I knew that paper, so yeah, thanks. And yeah, let me talk about the Focal-Planck equations a little bit. Okay, so like as I introduced, there are 2 processes in the diffusion model. The first one is forward process, which is given by the SDE, and this is a drift term. This is the diffusion term, and users can specify the FP and F and G by themselves. And once we given the for SDE, the forward process, it automatically corresponding to a backward SDE, where I also introduced. And also there is a deterministic process, which is the probability flow ODE, share the same density as the SDE. And why they share the same density evolution is actually because of the Focal-Planck equation. The Focal-Planck equation in classic sense is written as this. It governs the evolution of the density with time. And you can see that once the forward process is given, like the equation, the coefficient of the equation is actually fixed. Okay. And in our FP diffusion work, we found that indeed for the score function means this guy. For this score function, there is a PDE structure that the score needs to be satisfied. And we called it as the score Focal-Planck equation, which is in this format. So roughly speaking, it is dynamics describing how the score function, which is a vector field, evolved through times. Okay. So the first thing is the ground truth score, this guy, should satisfy the score Focal-Planck equation. And how we get this is actually like manipulate over the classic Focal-Planck equation and then write it as the score function. So we found that for the ground truth one, it definitely need to satisfy score Focal-Planck. However, the question is like whether the existing pre-trained diffusion model would also satisfy that score Focal-Planck equation. Which means for like off-the-shelf diffusion model as data, we want to check whether the errors of the score Focal-Planck equation will be 0 or not. So we grab some like pre-trained models, say like the pre-trained model on Cypher 10 datasets and also on MNIST. We found that actually the pre-trained models do not need to are not satisfying the score Focal-Planck equation. So you can see the blue curve. The scale comparing to the diffusion model training loss, which is in the orange, is actually quite large. And this phenomenon happened across different type of 4 SDE and also these 2 simple data sets. Okay, so here rise the questions. Because the ground truth should satisfy the score Focal-Planck, but the pre-trained model are not satisfying. So what's happened? And which means like why it makes the score Focal-Planck equation would not be satisfied by the pre-trained models. And the second question is like, what the benefit of satisfying score Focal-Planck could bring us. So in our FP diffusion paper, we are trying to answer these two, and I'm going to share it with a kind of bird view of our propositions. So we want to understand in first, like what happened if we can reduce the score Focal-Planck errors of the diffusion models. We first found that actually it can improve the data density of the data density determined by the probability flow, the deterministic process. And the second thing is like we found that reducing the score Focal-Planck error can make the diffusion model itself more conservative. The conservativity is in the mathematical sense, which is like it is close to some gradient of scalar function. And the last one, perhaps I won't touch it, but we found that if we impose the score Focal-Planck, it can make the density learned by the ODE and also the density learned by the SDE close to the ground truth. And it is actually quite intuitive because the ground truth should satisfy the score Focal-Planck, and once we impose them, once we impose the equation, then for sure we somehow need to get more it gets something more close to the ground truth stuff. And the last proposition is like we're studying why the pre-trained diffusion model would not satisfy the score Focal-Planck equations. But I will just focus on these 3 propositions. Okay, let me start with the first one. Why imposing score Focal-Planck equation can make the diffusion model better in terms of the data estimation, the density estimation. So before I jump into the details, let me still recap this picture again. Like we want to model the complicated data distribution by manipulating the simple product distribution with neural network. And in this case, we are doing the manipulation by this empirical probability flow ODE. The empirical means we plug in the neural network parameter score. So overall, this ODE will determine an density, which is denoted by PODE. And 0 means time 0, and data is the parameters. Okay. However, in the diffusion model training, it doesn't making sure that the density driven by the ODE needs to close to the data. So there is a missing part of the here. And we found that if we if we want to make the ODE determine density close to the data, we have no choice to impose higher order informations. And the higher order information, the first candidate is provided by the score Focal-Planck. Okay, so I'm going to explain this. Okay, like this is our probability flow ODE, the empirical one, where we use the neural network parameterized score as this. And if we start from the prior, this dynamic, this ODE dynamic will determine a density starting from the prior and with different time. Here I illustrated with the discrete time, but it doesn't matter. Like with the different time, we will have the density like this. So what we care about is actually this one, which is the clean data density. However, as I mentioned, in the diffusion model training itself, it doesn't really match the PODE 0 match this guy with the data density. And we found that indeed we need, like if we throw in the score Focal-Planck into the training, what I mean is like reducing the error of the score Focal-Planck equations. This guy can be matched better to the data density. So we have this proposition saying this in the KL sense. That is, the ODE determines.
Can I ask a question?
Oh, yes.
Why is that surprising? Because in my group, that's what we're doing. We're doing physics-informed neural networks, which basically that's exactly what we're trying. We're trying to minimize that residual, what you call error, we call residual. So
yes,
by minimizing the residual, you have physics informing the process, and therefore you expect, in fact, we can get also initial densities like that. That's something we have. So it's not surprising.
Yeah, it is not surprising, but it is also interesting that for the diffusion model itself, it has nothing to do with the density and the ODE density, because the loss function itself is not really directly related to the density estimation.
No, not directly, but it is related.
Yeah,
so, you impose the physics, you're going to get better answers, including initial guesses. I have another paper with Daskalakis from MIT where we show that actually that we can get the initial densities by imposing the physics.
Yes, and that is the missing part in the diffusion. That was the missing part in the diffusion model actually. Like they didn't impose any physics into it. And this stuff is, like you say, imposing the physics into the diffusion models. So of course you will make the density estimation.
Yeah. Please continue.
Yeah. Okay, so like if we make the score Focal-Planck errors like smaller together with the diffusion model training loss, we can ensure that the density estimation given by the ODE will lie closer to the data density. And this is also tested empirically. So let me briefly introduce what we did. Like this is the classic denoising score matching loss, And what we do is like imposing the score focal plane error, which is exactly doing the pin. So after we adding this regularizer, which is enforcing the physics stuff, we found that like this is the true data density, and the figure B is from the vanilla diffusion models. You can see that the density estimation is quite inaccurate over here compared to the data. But once we impose the focal plane equation, the score focal plane equation, we indeed can improve the data density like this. And for different toy examples, we also observe the same thing. Like this is the pictures shown over here are all density generated by the vanilla diffusion models. Take this for example. It's supposed to be uniform distributed on the checkboard. And also for this Swiss roll, it's supposed to be uniformly distributed on the Swiss roll. And for this one, which is the A Gaussians, it's supposed to be like a circular stuff, like expanding, like just like a Gaussian. But you can see that the vanilla diffusion model didn't do well on this, even on these two, even on this simple toy examples. But if we impose the the focal plane, I mean the score focal plane ratio, the density estimation is getting better. And yeah, I mean, this is the quick remark of this. Like imposing the score focal plane can get a better density estimation from diffusion models. And same for more like a complicated data set, like MNIST or FashionNIST, and also larger data sets of 32 by 32 by 3 scale. We consistently observe that it can improve the density numerically. Okay. And the other thing is also not surprising. Like in the score, in the ground truth score, this is the ground truth score. It is conservative, which means it is the gradient of some real value function. And in this case, the real value function is the log density. So for the ground truth score, it is conservative vector field. But for the diffusion model itself, it is not necessary to be conservative. So we found that if we impose the score focal plane equation, I mean making the ratio smaller, it will be approaching to some conservative vector field. And not surprisingly, this also can be demonstrated in numerical results. Like the red curve is the ground truth score, and you can see that the MSE of the curls. I mean, this is a toy example, which is in 3-dimensional case. You can see that curls is almost 0 for the ground truth. And if we impose the score focal plane with different weights, the conservativity is improved. Okay. And why it is important is because like the score, the diffusion model itself is actually implicitly related to the energy-based method. Like the energy-based method is trying to model the density with like brutally constructing something similar to the density, where the density need to be positive, so it take the exponential over here, and the density need to be scaled over 1, so it divided by some normalizing constant. So the score, the diffusion model itself is somehow related to the energy-based method, but the connection is not quite clear. And the not quite clear sense is in that the diffusion model itself is not parameterized in the conservative way. But with the score focal plane, we found that it can bring us some implicit connection with the classic energy basement. Okay. So up to this point, I explained two implications of satisfying the score for the Focal-Planck equation. And now come with why. Why? Let me skip this. Here come with why the pre-trained diffusion models do not satisfy the score for the Focal-Planck. So the simple reason is because the diffusion model training, which is by denoising score matching, is actually missing the higher order term, the higher order information. So what does it mean? Is like the diffusion model training is only trying to optimize this one, which is the zero order, I mean the slope. But we found that indeed, if we can do the higher order, I mean the gradient of the score and the second gradient of the score, if we can match this as well, then it can reduce the score Focal-Planck error. And this proposition gives us an explanation why the diffusion model itself does not satisfy the score Focal-Planck, because it only injecting this during training. Okay, so here is roughly the end of my first work about the diffusion, and I guess let me stop here a little bit, and I will show you something which might be more interesting. So, any questions so far?
Do we have any questions from the audience?
Excuse me.
Yeah,
may I have a question? Yes. So when you try to matching higher order scores here, well, from my knowledge, that's the when we try to learn the score functions, you do know the theta. Try to approximate the lambda of the log. But for the higher order information, how do you know the S?
So here we cannot. Actually, for the zero order, we also don't know the S. So we need to use the so-called the condition. I mean the denoising score matching, which is we condition on the data and then perturb by noise. And in,
so in the high dimension, you also do something like that. Try to do some asymptotic stuff. Oh, okay. So there are some details just didn't put here, right?
Yes.
Okay. Thanks.
Yeah.
Is there somewhere in your paper the details of approximately higher order derivatives?
In our paper, we do not directly impose these higher order derivatives, but we directly impose the score Focal-Planck error to be zero, which is solving the ping. Yeah.
Oh, so you kind of directly do the ping training instead of using these.
Yes.
Okay, I see. Yeah, thanks.
Yeah. It's like pin training. You're right.
Yes, it just pin training. Actually, I skipped my training loss. I just quickly show the training loss. So the training loss is over here. Like this guy is actually the pin.
Oh, okay. I see.
Yes. Yeah. So the FP diffusion.
Sorry. Do you use any weights in front of the losses, or just add them like that?
Yes, I use some weighting.
Because I saw in one of the plots you have different W's, right? You have different values of in one of the plots where you have they were showing towards the graph.
Yes. I use different weights.
I guess that's his alpha and the beta.
Yeah. I use different weights. And what is okay? So the thing is like, if we impose too much on the score Focal-Planck, I mean the weights alpha is too large, it totally destroys the diffusion model training. And so for for like a practical like implementation, we should use the score Focal-Planck error to be small. I mean the weights to be smaller, which means the pin's information is actually smaller. However, what is interesting is like this. Let me skip. Let me jump to here. As the lab here is the kind of where the pins coming from. So let's talk about something more pins. Like the diffusion model was using this kind of training loss, which directly used neural network to approximate the score function, right? But from our score Focal-Planck equation, we actually provide another point of view of training, possible way of training diffusion models, which is solving pins. So in principle, we can get a score, this score function by literally minimizing the score Focal-Planck error, which is doing the pin stuff. And I tested on some simple examples, toy examples, where we know the data density, we know the closed form of it, and also we know the closed form of the score. And do the pin training where this is the PDE and this is the initial condition. Okay, do the pin trainings like this. And we found that indeed the samples, the ODE determined density can well estimate the original one. So this is quite interesting, at least to me. That is perhaps for the diffusion model training, we can use some we can just use some pins instead of doing this kind of denoising score matching. But the nuance is like this. We here assume we know the data, the structure's data density at time 0 as the initial condition. But for the real implementation, more complicated data sets, we have no knowledge about this. So there are some ways that we perhaps can prevent from knowing the very clean data information by, say, you perturb it a little bit and still take it as initial condition and solve the pin. But I found that it doesn't work. So here is another interesting direction to dive into this. That is how to, say, use the pin solving idea to deal with the diffusion model training. Okay. So far so good.
Yes, great.
Excuse me, I have a question.
Oh, yeah.
Hi, this is Panos Thinis from Pacific Northwest National Lab. So when you use just the pin part of in your loss function, you are enforcing agreement for the residual, right? How well you satisfy the equation.
Yep.
However, when you actually use the DSM, right, the JDSM, you enforce agreement of the score function itself.
Yes.
So, and in order to just train with the residual, meaning the pin part, and get convergence for the actual function, you need some kind of extra control on the properties of the equation, something like kind of a stability argument. Mm-hmm. So here, when you have a diffusion model, you have a forward process and a backward process. So if one of the two is stable, the other will be unstable, right?
Yes.
So all I'm saying is that you have to be careful if you only use the pins, because you don't know how stable is the step that goes from noise to the data distribution.
Yeah, exactly.
If it is unstable, training just with the pins will not be enough. You will also need what you have the second term there, which is the value of the score at time 0.
Yes, exactly. Yeah. I also agree with that. And thanks for the comments. Yeah.
Yeah. Okay.
So
Thank you.
I also do believe merely training with pin is not enough. So this is why the score Focal-Planck still needs this kind of, I mean, the FP diffusion still needs the denoise information to kind of stabilize it.
Exactly. Yes. Yes.
Yeah.
Yes. Yeah. Okay. Thank you.
Yeah. Yeah. Thanks. Okay. So I guess I don't have enough time, but yeah. So I would love to take more questions. If no, yeah, I guess I only have 10 minutes, right?
Yes, but I think you can keep going, right, George?
Yes, sure.
Okay. Okay.
Yeah, take your time.
Okay. Cool. So, like I say, there are different kind of consistency concepts. The FP diffusion, I mean, our FP diffusion is one of them, and there are several from different institutes doing the different things, and they are actually equivalents. Yeah, I guess this part may not be so interesting, but let me jump directly to this guy. I mean, the CTN, which is still the fast sampling. Yeah. So just briefly, yeah, let me first skip this. Yeah, so for just a very high level idea of what we are doing to make the diffusion model sampling fast, it's like this. So as I mentioned, there are two issues of the diffusion model. The first one is inaccurate during the small time training, and we somehow fix it with the FP diffusion. And the second issue is like the sampling is always slow because essentially it's doing the SDE solving, the ODE solving. But thanks to the SCORE SDE paper by Yang Song, it brings a lot of study into making the ODE solving faster. So classical way, like higher order gradient to approximate the trajectory. You can use adaptive step size, extrapolation, whatever approximation to make the ODE solving more accurate and also fast. So there are a lot of papers to doing this, as you can see over here. And what I want to introduce for our solution is called the consistent trajectory model. In a nutshell, it can achieve the SOTA level, I mean, in terms of the generation, with only one step. And also, it unifies the diffusion models itself, and also the long jump along the solution trajectory. So what I mean is like this. Here is the initial condition, and this is the solution trajectory defined by the ODE dynamic. And what we are doing, the CTM, what CTM is doing is actually learning the jump from any point to any point. So say from T point to any S point. And the T and S could be arbitrary as long as T is greater than S, where T is the initial and S is the end. So what the benefit of doing this? So if we can really learn this kind of any-to-any jump, then when S at the extreme case, which is 0, then we can directly jump from a noise to the clean data. And then we can do the one-step generation. So this is one perspective. The second one is when S is very close to T, then it gives us the slope information. And the slope information, of course, going back to the diffusion model, because diffusion model essentially is learning the slope of the trajectory. So with our CTM, we actually can unify the diffusion model and also the fast sampling model, which is doing the any initial point to the claim. In a mathematical way, we are actually learning the semi-empirical structure of the result. So the model itself contains the starting point, the starting time, and the end time, and it produces the end points. All right, so I guess I don't have enough time to go into the details, but in the high-level ideas, our CTM is making the different model sampling fast, address the second issues, and our FP diffusion is making the different model training more accurate, which address the first issue. And I'm going to end my presentation here, and let me go to my information here. So yeah, thank you very much for having me here, and you can reach out to me through these manners, and happy to collaborate or communicate.
Oh, okay. Great presentation, Jesse. Thank you so much for your time. This was really informative.
Jesse, can you show some results for the last part? Maybe at least one result. Are you jumping all the way to make a single jump, or how many jumps you have to do? Just you give us the teaser, but you didn't show any results.
Yeah, let me show the result. So, okay, let me show this. The left-hand side is the pre-trained diffusion model, where they use the Quinn's solver, I mean the second order solver with 79 steps. And the right-hand side is our model, which is called the CTN. You can see that, I mean, it is with one step. You can see that the kimono, which is the traditional Japanese clothes, you can see that the detail is more fine-grained. And yeah, this is for the illustration.
Is it 79 times faster, or is it 10 times faster?
Not linearly in time. Not linearly in time.
In this example, how much do you remember? How much faster were you?
Yeah. So, for roughly speaking, the diffusion model takes few minutes to generate one image, and the one step CTM, which is our model, will take only I mean within the second actually. So yeah. And the resolution of this image is 64 by 64, which is quite tiny, but if you scale up, the difference may be quite getting larger.
Great, yeah.
Yeah, and more results like this. The middle two columns are our CTN, and we use one step or two step jump. And you can compare to the teacher, I mean the diffusion model, which uses 79 steps. And I mean visually, the CTM with one or two jump can get more accurate than the diffusion models. Yep.
Great, thank you.
Yep.
Do we have any other questions from the audience? It looks like we do not. There were a lot of questions in the middle.
Okay.
Okay, Shuhao and Jesse, thank you so much for your time today. And as always, we will publish these videos to YouTube, so you can go over your presentations afterwards, and we will share with you the links.
Okay, cool.
Okay,
thank you very much, Jesse. That was great.
Yeah, thank you so much.
Great. Thank you everyone for your time today, and until the next Crunch seminar.
Yeah, thank you.